Okay, this is your turn to have a go at some exam questions. So pause the video, have a go at these. They're all fairly difficult, but certainly question 3, part C, I would say, is probably the A-star level. Okay, here we go. Question 1. Now, I think a lot of students reading this would be a bit intimidated. There's a lot of writing. It's presented as one student says this and another student says that, and the discuss is a bit intimidating. In actual fact, this question is not as difficult as it appears. And the tip I would give you here is, if you're unsure how to answer a question, write out the formula which is related to the topic, in this case, internal resistance, and just have a go, see what you can calculate, see what you can work out. Okay, so let's work through this. So it's a 5-mark question, which in itself can be a bit intimidating, but it's a relatively easy approach once you know what you need to do. So it says a voltmeter is connected across the battery. Okay, so that we need to work out that a voltmeter will give us the best approximation of EMF. So 1.45 is the EMF of the battery after it's been used for a few weeks. So just identifying that will give you 1 mark. So maybe you can do that. This is also a good reason for laying out your answer with clear working. So if you just write 1.45, you wouldn't get any marks. But if you say the EMF is equal to, then that's 1 mark. Okay, so then we're told that we've got a resistance of 5.32. That's the circuit resistance. And we've got a voltage, 0.85. So even though the calculation here is quite straightforward, there's a little bit of understanding required. So we need to know that the 5.32 is the circuit resistance, capital R, and the 0.85 is the terminal PD, or the circuit PD, which is capital V. Once we figure that out, then it's a simple calculation, I is equal to V over R, and we get 0.16 amps. So then we can use the formula, the internal resistance formula. We know everything apart from the internal resistance. So we're trying to find the internal resistance after a few weeks have passed using this data here. So it's the EMF take away the terminal PD divided by the current is 3.75. Okay, if we've done all that, that will give us 4 marks. The discuss, always a bit of an intimidating word. It's just make some comment or evaluate or make some relevant suggestion related to or comment related to what we've been asked to consider. So they're actually both correct. So we've proved that the EMF has reduced because we've identified that's 1.45. So the EMF has reduced, so student 1 is correct. And also we've shown mathematically that the internal resistance has increased. So student 2 is also correct. So some kind of comment would get the 5th mark there. Question 2. So voltmeters should have a high resistance. So typically multimeters, you may have used one of those. They have a much higher resistance than just normal classroom voltmeters, because that gives us a better reading and a closer approximation of the EMF. Why is that? Okay, so if we have a high resistance, then the current through the voltmeter is going to be small, I equals V over R. If the current through the voltmeter is small, that means the current in the circuit is small, if we're just measuring across one component. And we know that I times little r, well, assuming that the internal resistance is fixed, if we have a small value of current, I times little r will be small. We know this is the lost volts. So the smaller the current, the smaller the lost volts. And then the reading we actually get on the voltmeter, which is our circuit PD, is going to be equal to the EMF take away a small value. So we'll never get exactly the EMF on our voltmeter reading, but we can get as close to it as possible by decreasing the lost volts. If you think conversely, if you have a voltmeter with a low resistance, therefore a large current is going to go through the battery, then we're going to have a larger lost volts, and therefore we're taking away a bigger value from the EMF. So the exam tip here is always, where possible, make reference to a formula in your answer, because that gives you, I suppose, more confidence in your answer, and it also ticks a box for the moderator to convince the examiner or the moderator that you know what you're talking about. Question 3. So there's no circuit diagram given here. Maybe you'd get one in the exam, or possibly not. So certainly the first thing I would do is draw a diagram so you can visualize what's happening. And I think just general tips, especially this is relevant for part C, always have a go, always show you're working, always look at the marks. So 3 marks for this one. A common mistake for this one might have been to think, well, that's 12 volts, so it's going to be 12 volts and 12 volts. But that's not taking into account the internal resistance. So if it was a 1 mark question, then maybe it would have been that simple. But for 3 marks, it's not just going to be, oh, it's 12 volts. It's going to have to be more difficult than that. And in fact, there's a couple of stages here. So always have a go. So see what you can work out. So we know 4 ohms and 6 ohms, we can find the resistance of the parallel section using our standard approach. Don't forget to invert your answer. As always, the total resistance of the parallel part of the circuit should be less than either of the individual values. Then we can use the internal resistance formula. We need to find the current because we know the EMF and we know circuit resistance is 2.4 and the internal resistance is 0.6. So we can calculate the current is 4. And if the total current is 4 amps, what we're saying, well, we could work out the loss volts if we wanted to. We don't need to in this case. We're saying that the current through the entire circuit, the actual circuit down here, is 4 amps. So the voltage across that will be I times big R. If we know the current and we know the resistance of the parallel section, so we're going to treat these two effectively as one resistor, if that helps you visualize it, and we end up with 9.6 volts. So we would have expected that the circuit PD, which is the potential difference across the parallel resistors, is less than the EMF because the EMF is the ideal maximum theoretical value, and we will always get less than that because some of that 12 has been used up as loss volts. Part B, we need to find the power dissipated. So this word dissipated is quite often used. It's just the power across or associated. And this should be relatively straightforward. It says 2 marks. So that would suggest it's a little bit more straightforward. We've got this formula in the formula booklet. P is equal to I squared R. And we know the current is 4. We know the internal resistance is 0.6. So that's a relatively straightforward question. 9.6 watts. Now, potential confusion here. You might think, why is that the same as the voltage? This is just how the numbers work out, which I think is a little bit annoying of the question to do that, because you might be thinking that doesn't sound right. But if you've shown you're working out and you've done the maths correctly, then sometimes the numbers are just not as expected. There's no reason why it would be 9.6 watts. This is just how the numbers work out. Okay, so part C, if we replace R2 with a variable resistor, then what value of R2 would minimize the total current? Justify your answer. So this is a difficult question and difficult to get 4 marks as well. So we do need to make reference to more than one formula in this case. We know that I is equal to V over R, or the EMF divided by the total resistance. So we could think about this expression here. Total resistance is internal plus circuit resistance. We also know that the resistance of the circuit, which is the parallel section, is equal to 1 over R1 plus 1 over R2, and we invert the answer. So we could make a comment like, if we're going back to this expression here, if we want I to be as large as possible, we can't do anything about the EMF, that's 12. I want to reduce the circuit resistance, or the total resistance, as much as possible. There's nothing I can do about the internal resistance, so I need to reduce big R as much as possible. So we're looking at this expression here. So R1 is fixed. What can I do to R2 to make this overall circuit resistance as small as possible? And you should be able to work out that if you increase the size of R2, then 1 over R2 is going to start getting smaller and smaller. So you want R2 to be as large as possible. Now we would say ideally an infinite value. Now, infinite is, you might think, an impossible number to achieve, but it would become effectively infinite if we have a very, very large value, as big as we can possibly make it. So then we need to explain, well, why is that? So just to go through the full explanation. If R2 is as large as possible, then 1 over R2 approaches 0. Therefore, we've effectively eliminated R2 from the circuit. We've made the total resistance of the circuit as small as it can possibly be. Therefore, the current will be as large as possible.